Here's a fraction raised to the fourth power. But since the fraction n over 2 can also be considered to be n divided by 2, we can also call this a quotient raised to the fourth power. Well, from what we know about exponentiation, we can write it like this. And then, from what we know about multiplication of fractions, we know that we can multiply all the numerators together to get n to the fourth, and all the denominators together to get 2 to the fourth. And of course, 2 to the fourth is 16. So the preferred way of writing it would be on the bottom, n to the fourth over 16. Here's a more complicated quotient. 5n on the top over 2a on the bottom. And that's all taken to the third power. Once again, from what we know about exponentiation, we can write it like this. And then, from what we know about multiplication of fractions, as well as the commutative property of multiplication, we can rewrite it as shown in line 3. Then we multiply 5 times 5 times 5 in the numerator, as well as 2 times 2 times 2 in the denominator. And then we know that n times n times n is n to the third, and of course a times a times a is a to the third. And we get 125n cubed over 8a cubed. And that brings us to this rule, the power of a quotient. Exponentiation distributes over division. That is, for any real numbers x and y where y is not 0, and for any integer a, x over y taken to the a power is the same as x to the a power over y to the a power. And now we're going to apply that rule to make simplifying this expression go a little quicker. We make some red marks to show what's going to happen when we distribute our exponent throughout this quotient. And it applies to both factors of the numerator and both factors of the denominator as shown in line 2. And then, of course, 5 cubed is 125 and 2 cubed is 8. And our expression in line 3 is the same as it was when we did it the long way, only this time we've applied the power of a quotient. Here's another expression, n to the 8th power over n to the 5th power. It can be rewritten as shown because of what we know about exponentiation. And then, from what we know about simplifying fractions, we know that every time we have a number in a numerator and the same number in the denominator, that means the number divided by itself, which is 1, so they can both be marked out to be 1s. Once again, provided that n in this case is not 0. But when we write an expression with a variable in the denominator, we assume that the entire expression has a value, so we assume that the denominator is not equal to 0. So we're marking out as shown. There's the first 2, the second 2, the third pair, the fourth pair, the fifth pair, and now all 5 n's in the denominator have been marked out, each one pairing up with one of the n's in the numerator, leaving 3 n's in the numerator, n times n, or n to the third, also known as n cubed, which is a simpler way of writing n to the 8th over n to the 5th. But you may have noticed that the 8 and the 5, when subtracted, equals 3. And yes, that's going to lead to a rule. But before we get to that rule, let's look at one more expression, a little more complicated than the last one. We're going to write it out the long way as shown. And then we know that the 12 and the 8 are both divisible by 4, so they can be marked out to be 3 over 2. And then we've shown all our work at once, but there was just one m in the denominator, so it marked out with one of the 6 m's in the numerator. And there were 3 n's in the denominator, so each one of those paired up with one of the 4 n's in the numerator. And then we look carefully and we realize that we have a 3 and then m to the 5th and an n in the numerator, and just a 2 times 1 times 1 times 1 times 1, or just 2 in the denominator. So we write it as shown. 3m to the 5th times n over 2 is much simpler than the original expression at the very top. And now, before we get to the next rule, notice I've added a power at the very top in red because the m is, of course, the same as n to the first power. And then notice 6 minus 1 is 5. And also notice 4 minus 3 is 1. Now, originally there was no 1 at the bottom, but I've added it in red because an n and an n to the first power are the same thing. But of course, in our final answer, we prefer to drop the power of 1 and just write an n instead of n to the first power. Now let's look at our latest rule, the quotient of two powers with equal bases. If you divide two powers and they have equal bases, then you can subtract the exponents, numerator minus denominator, for any non-zero number x, and for any positive integers a and b, x to the a power over x to the b power is equal to x to the a take away b power. So let's take a look at this previous expression, and now we'll apply our rule to make it go quicker. We remind ourselves that an m is the same as m to the first power, and then we write 12 times m, and then we write 6 minus 1, and n to the power of 4 minus 3. Of course, the 12 and the 8 mark out to make 3 over 2. 6 minus 1 is 5. 4 minus 3 is 1. And then on our final answer, we remove the 1, and we're left with the same expression we had when we did it the long way, 3m to the 5th times n over 2. Here's a review of the two rules from this lesson, the power of a quotient and the quotient of two powers with equal bases.